Natasha Abrams is a fifth-year astrophysics PhD student right here at UC Berkeley, searching for black holes via gravitational microlensing. She's completed her Bachelor of Arts at Harvard University in 2021, and she works on photometric microlensing with large surveys, astrometric microlensing, and understanding how binaries impact our statistical understanding of the events we discover. She is passionate about pedagogy and mentorship, both in research and broader academic settings. So please, Natasha, give your talk. And you can
All right, everyone. Hi. We're going to be talking about black holes, discovering the invisible. So first off, what is a black hole? A black hole is a point of immense density and its effects around it. It can curve the space-time and around it, and that's described by general relativity. And it's so massive that even light can't escape its gravitational pull. Let's talk about the anatomy of a black hole. So at the middle, you have this point, the singularity of immense density. And then around it, you have the event horizon. That's the radius past which light can't escape. So what I mean by that is that, so we have such thing as an escape velocity. So when I'm sitting here on Earth and I jump, and I go flying off into space, Earth's gravity pulls me back down. But if you have something much faster, like a rocket, that can escape Earth's gravitational pull and go off into space. In the case of a black hole, even light is not fast enough to escape its gravitational pull past this event horizon, and that's why it appears dark, because light can't get from it to our eyes, and so we can't see it. Light is also the fastest thing in the universe, and so nothing can escape a black hole's gravitational pull. And so I'm going to be talking about a lot of different ways that we go about discovering black holes, and talking about the discovery of individual objects. And when we discover these objects, discovering the individual black holes help us to piece together an understanding of black holes more generally and physics in our universe. Black holes are at the forefront of our physics knowledge, and so understanding black holes, how they form, how they evolve, their distributions, like how many of them are there of a certain mass, can help us better understand our universe. So first I'm going to be talking about astrophysical black holes. These are black holes that come from exploding stars, stars that have evolved, and they're at least 10 times more massive than our sun, that will explode and leave behind a black hole from their core. And so how do we detect these stellar mass black holes? And they're just called stellar mass because they're around the mass of our sun. So we'll be talking about a few different techniques, ordered in this sort of way. So the way that we detect stellar mass black holes, the ones that are easier to detect tend to be those that are actually in less common of configurations. So we're going to be talking about those that are easiest to detect, that are least common first, and then going to those that are more common but harder to detect. Or to be clear, this isn't actually necessarily true a priori. We wouldn't necessarily expect this beforehand, but this is what we find for stellar mass black holes. So first I'll be talking about X-ray binaries. So these are systems with a black hole with a stellar companion. And so by this I mean you have a binary where they're orbiting one another. They're caught in each other's gravitational pull, the same way that Earth goes around the sun. The black hole and the stars go around one another. And so in the case of this, you have a extremely large star that's so large that it has hard time holding on to its outer layers of gas. And so when the black hole goes nearby it starts to accrete the outer layers of that gaseous star nearby, which forms a disk around the black hole. And so you end up with the disk of all the outer layers of that star going around the black hole. So how do we detect this? And that's because this gaseous, it's called an accretion disk, actually starts to glow. So the way that you can think about why it does this is that for the same reason that when you rub your hands together, the friction starts to heat up your hands, there's also gas friction that starts to heat up the gas. And so this makes it so that the gas in that accretion disk tends to glow in the X-rays. These are the same sort of X-rays that are used if you go to the doctor and you break your arm to be able to look at the bones in your arm. These are the energetic light that is coming from the accretion disk. And so about 20 of these black holes have been found, about 3 times the mass of our sun to about 23 times the mass of our sun. And most of them were found in the 1970s. And so systems where there's a star and a black hole that are so close together that they can interact in this way are very rare. Next, I'll be talking about black hole systems. So that's when you have 2 black holes that are orbiting one another. And these are, so the way we detect these is from gravitational waves, from when these black hole systems merge together. These are also, on a universal scale, quite rare. So the way that this works is that as the black holes are going around, their orbit starts to decay. They've started out farther out, and they start to get closer and closer and closer until they merge. When they merge, the orbit decays, energy is released from that orbit in the form of gravitational waves. You can see in this artist rendition the ripples in space-time that are created from the black holes merging together. And so this, yes. And so this emits the gravitational waves, which we can actually then observe. So when we observe this, this is the sort of thing we hear, sort of. Let's see if this works sound-wise. So it seems that the sound is a little hard, so I'll reproduce the sound. It goes whoop, whoop. Right, there's that slow rise and then a quick, it's called chirp. And so that's when the black holes are out spiraling around, getting closer, closer, and merge. And that corresponds to that chirp that you can see here. You can see here, and would be able to hear. And so when the gravitational waves are being created, they're actually changing the space that we're in. They're pulling and pushing the space together in this way, and then another mode is kind of in an X way. And if they were at a much larger amplitude, you would be able to feel them. Of course, they're a very small amplitude, and so it's very it's difficult to measure, and you wouldn't feel them, but the gravitational waves are coming through where we are now. The way that we do measure them is by using LIGO, or the Laser Interferometer Gravitational Wave Observatory, along with other gravitational wave observatories around the world. So what laser interferometry does is that you have somewhere in the desert this facility with these 2 really long arms. And the reason why you do that is that you have this sort of system. So in this system, you have, I'm going to use this. You have your laser shining in. And then what you have here is what's called a beam splitter. So you take the laser light and you split it in half. And you send half of it down one arm, half of it down another arm. It then goes to the end, it hits mirrors, then it comes back together, and then we interpret what's happened. So laser light is what's called coherent. And so all of the light together is going together in a wave like this. Then when it hits the beam splitter, it splits in half and goes down the two arms, hits the mirror, and then comes back together. And if nothing has changed in the space between them, then the light will just keep going together in a coherent way. But if the space has shifted, if it has gotten smaller and larger as it went, then as it goes, it'll be going together, it'll split, and then one arm will start to go in one direction and the other arm in the other direction. And then when they come back together, they'll interfere. And so instead of being together, they'll be in a different way. And so you're able to tell that the space has shifted in a very, very small amount. And so we're able to detect gravitational waves that way. And a few hundred black holes have been found. So this is the most updated results from the data release last week of the gravitational wave observatories. So the way to interpret this plot is that we have on the x-axis is totally meaningless. It's just to distribute the objects. On the y-axis, it's the mass of your objects. And so you can look at one system, and we can see here, so you can see one dot and then another dot above it. These are the two initial black holes. They merge together to form a black hole of this mass. And so, for example, here, this would be a black hole of about like 7 times the mass of our sun, plus one that's about 10 times the mass of our sun, merged together to form one about 18 times the mass of our sun. You can see here that even just from measuring these objects, we've learned a lot about black holes and about how they can form and stuff like this. We're really pushing the boundaries of the types of black holes we thought could exist. So that one all the way up there, above 200 times the mass of our sun, we thought that it was really difficult to form or impossible to form black holes of that size. Certainly from just stellar evolution, you need other things like black holes merging to form other black holes, merging to form more black holes, stuff like this. And also pushing the boundaries of what we understand on the smallest size of our black holes too. So next, we're going to be talking about using astrometric wobbles to find binary black holes. So these are much more common. Instead of black holes being in a system with another star, where the star is really close and they can interact with each other, or two black holes that are really very close such that they're merging together in our lifetimes. Instead, this is like a black hole and a star just happily going along for millions of years. And the way that we detect these is that you can measure really precisely the position of your star going around seemingly nothing. And we can measure that and determine the mass of the object that's going around. If it's much more massive than our sun, but we can't see anything, then you can determine that it's in a binary of the black hole. And so 3 black holes have been found this way so far. So they're all these called Gaia black holes because Gaia is the telescope that's out in space that did all the measurements of these objects. And they're all found within our own galaxy, within our Milky Way. And so this is a representation of where in the Milky Way they were discovered. So next I'll be talking about gravitational lensing. This one's near and dear to my heart, as Daniel mentioned. This is what I studied day to day. And if you were here back, I think in April, Macy Houston, a postdoc in our group, also talked about this. And so the way that, so gravitational lensing is when you have a massive object that bends the light of objects behind it and its line of sight. So you can see here, you have some galaxy in a cluster that's bending the light from some other distant object, which is probably a galaxy, and you get distorted images of that distant object, which we then can see from Earth. And so here's an actual image of a red galaxy acting as a lens and a blue galaxy behind it, that they're nearly perfectly aligned, so you get the lensing of that distant object. In the case of microlensing, gravitational microlensing, we usually can't actually resolve those distorted images, and they're moving with respect to one another. And so we're using this to study objects on a galactic scale. So this is within our own galaxy, black holes and stars. And I guess to clarify, a galaxy is made up of lots of stars and black holes. And so in this representation, the yellow is the lens. So this would be the black hole, but it could also be a star or any other massive object in our galaxy. And then in red, that's our source star moving behind it. We're right now pretending that the lens isn't moving. And then in blue are those distorted images of that distant object. So in the case of microlensing, we can't what's called resolve those individual images. So if you can imagine, I could be standing here with two flashlights. If you were up close, you could see that I had two different flashlights and you can see their individual beams. But if you were on the other side of the room or on the other side of a football field or something like that, you wouldn't be able to see that I was holding two individual beams. Instead, you would just see that I'm holding one brighter beam, or that's maybe a little bit elongated. And so that's what's happening here. We don't, in most cases, we don't have the telescope power to be able to resolve those individual images. So instead, what you see is an increase and a decrease in brightness as the lens and the source move with respect to one another. And so what's really great about this is that we can use it to discover isolated black holes. So these are black holes that aren't in a binary at all. They don't have a stellar companion. They don't have a black hole companion, or they could, but they could also just be floating on their lonesome, just passing in front of some random unrelated star. And we think that most black holes in our universe are isolated, and this is the only known way that we know to discover them. And so black holes tend to lead to long duration microlensing events. You can think of this as the more massive objects tend to have a bigger area of effect as they move. And so then your background source, your star, is lensed for longer. And that's how we find black holes. However, with the photometry alone, we can't actually just say this event was caused by a black hole. And that's because there are other effects that are degenerate with the massive nature of the black hole. So for example, you could have a star that's moving really slowly, and that could lead to a microlensing event that lasts as long as a relatively fast-moving black hole. And so we need to be able to model these objects and these systems to be able to understand what sort of distributions of the durations of the events we get. So, for example, this shows the number of microlensing events as a function of their duration. And in red are the stars, and in black are the black holes. And you can see that there's a lot of overlap in how long the microlensing events are. So this isn't days. So this would be like the peak is around 20 to 30 days. And black holes peak closer to 60 or 70 days, but there's a lot of overlap. All is not lost for photometry alone, though. You can distinguish different models. So like different distributions of mass. So like, if all black holes were 1 times the mass of our sun, or if all the black holes were 100 times the mass of our sun, that sort of thing, or much more subtle versions of that, you would be able to see in this sort of model. And so you can see here the dashed line versus the solid line are 2 different black hole models. It's also not lost for individual microlensing events, because we can look at what's called the astrometry, so the position. So the photometry is the brightness over time. The astrometry is the position over time. And so this is the technique that was used to find the first isolated stellar mass black hole by Casey Lamb, who graduated from our department a couple of years ago, and is a postdoc, and Kailash Sahu at the Space Telescope Science Institute, about 6 times the mass of our sun. So let's talk about what the technique is. So this is a very similar graphic to what was earlier. In yellow is again the lens, which would be the black hole or the lensing star. In the red open circle, that's your source moving by. And in blue are the distorted images of your source. And so you can imagine, let's go back to the flashlight example. If I had 2 flashlights, if one flashlight were much brighter than the other one, you would probably see that like the sum of the positions were closer to the brighter flashlight when you're across the football field. And so in the same way here, this image above is brighter than this image below. And so then what you get is this filled in red circle, which is the centroid of the position that you measure. And so you can see there's a difference between the source position and the measured position. And so when you measure that little wiggle, then you can actually see, you can measure the effect of the lens having passed in front. And when you measure that signal along with the photometric signal, the brightness over time, then you can measure the mass of your lens. And as I mentioned, this was used to find the first isolated stellar mass black hole. And so to summarize, for the stellar mass black holes, we looked at these two, the X-ray binaries and the gravitational wave black holes, which are both relatively rare configurations, but easier to detect. And a middling black hole and star binary pair that are not interacting, a so-called detached binary, found using the astrometric wobble, the wobble of position, and gravitational microlensing, which can help us find isolated stellar mass black holes. So far, only one's been found this way. So next, we have a big gap in the mass of our black holes. Between about 100 times the mass of our sun and 100,000 times the mass of our sun, there's no black holes that have been measured. These are so-called intermediate mass black holes. And these objects, we have theories about, how the next category, the supermassive black holes, were formed, and people are looking for them, but at the moment, none have been found. So next, we'll move on to supermassive black holes. So these are black holes that are at least 100,000 times the mass of our sun, and they tend to be found in the center of galaxies. There's one at the center of our own galaxy. So this is an artist's rendition of the Milky Way, where there's a black hole in the very center of the galactic bulge at what's called the galactic center. So the way that this was measured, it's called Sagittarius A star. That's the name of the Milky Way's our black hole. So the way that it's measured is by looking at stars going around seemingly nothing at the center of a galaxy, zipping around seemingly nothing. So this is quite similar to the astrometric wobble approach that I mentioned for the stellar mass black hole, where the star is orbiting around nothing, but it's actually a black hole. This was the first where stars were measured over the course of 30 years to look at map out their orbit around the black hole at the center of our galaxy. So I'm going to play this video in a second to interpret this. This white star here is the position of Sagittarius A star, the black hole, at the supermassive black hole at the center of our galaxy. And these blue circles are all the stars, which orbits were measured by the Keck telescope. Let's play this. And you can see that all these stars are moving much faster than other stars that we see at this distance around this massive object. And so Sagittarius A star is about 4 million times the mass of our sun. In 2020, Andrea Ghez at UCLA and Reinhard Genzel, who's sometimes here at Berkeley, won the Nobel Prize for this in 2020. And that particular star is highlighted as its orbit. It's very well conceived. So next I'll be talking about the so-called picture of a black hole. Give me a show of hands if you've seen this picture before. Yeah, it's a very popular picture. And really impactful as well. And so this is the black hole at the center of M87. It's another galaxy, and it's 6 billion times the mass of our sun. So that is 1,000 times more massive than the black hole at the center of our galaxy. And so let's break down what we're seeing here. So this is a NASA animation of the black hole that we're seeing, that we then took the picture of. And I'll explain why I'm saying picture with quotation marks shortly. So let's break this down further. What we're seeing here at the center, this is the black hole's shadow. This is the point or the area that light cannot escape from. So if you remember, this is related to the escape velocity and the event horizon that I mentioned earlier. It's subtly different from that concept because the black hole is actually spinning, but you can think of them in a similar way. And then all this red area here is the accretion disk. So this is the disk that is going around the black hole, as I mentioned earlier with the X-ray binaries, right? There it accreted the matter from the companion star. It went around and formed an accretion disk around the black hole, which heated up, right? And then we could see and measure that accretion disk. And so that is where the light is coming from that we're measuring in this case. But this looks different than a disk. It's got this weird upper part and this lower part. And that's because of gravitational lensing, as I mentioned earlier. So the black hole is warping the space around it. And it's causing, it has that accretion disk going around it. And the black hole is lensing the back part of the accretion disk, above and below it. So the part behind the black hole, some of it's being lensed above, and some of it's being lensed below the black hole. So like say that the top part of the accretion disk were purple and the bottom part were green, then the top part would be green and the top part were purple, the bottom part was green, and the top would be purple and the bottom would be green when it's lensed. And so that's what you're seeing there. And then you can see that this side of the black hole is brighter and than that side of the black hole. And if you'll notice here, that's the side that actually is moving towards you, and the other side is the side that's moving away from you. And that's caused by what's called Doppler beaming. So this is related to the Doppler effect, which you've probably heard. Let's say when an ambulance goes by you or someone's playing music while they're on their bike or something like that, then you would hear, let's say in the case of an ambulance, be like, wee-oo, 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 when it goes past. And so this is because of the Doppler effect. And so in this case here, you can think of sound as a wave. where it's got peaks and troughs, and that is a wave in the air that you hear. And so you can imagine that the ambulance emits some wave, and then it moves. And then it emits another wave, and then it moves. And so as it's moving, the distance between each peak in the wave is going to become shorter because it's actually getting closer to the waves that it emitted. And a shorter peak corresponds to a higher pitch. In the case of light, it also corresponds to a bluer wavelength, and glossing over some things, a higher energy. And then as it's going behind it, it's moving away from the wave that it emitted. So then you end up with a longer wavelength, which corresponds to a lower pitch, a redder wavelength, and again, glossing over some things, a lower energy. And so that explains why you see this redder side over here, or sorry, brighter, bluer side over here, but orange is slightly more blue, and the on the other side, the less bright. And so how does that picture actually taken? So the reason why I'm putting picture in quotation marks is because there's no camera like you would think of. There's not even a camera mounted on the back of a normal optical telescope. What's used here are radio dishes. So this is a radio observation. So you have all over the world these radio telescopes, which are basically like, if you imagine the satellite dishes for television or something like that. And so each point on this map corresponds to a position of one of the telescopes that was used to take this data. And so the reason why they do that is so that they can essentially make a telescope that's the size of the Earth. There's a lot of empty space in between. So the way that they do this is every pair of telescopes is connected by a blue line here. And each pair of telescopes corresponds to a point in this space here. So this is called Fourier space. And you can think of it like the information space necessary to create an image. And so the reason why there are curves in this space instead of points is that the Earth is turning. And so the actual distance between each point, each pair of points in this image changes a little bit over the course of then they take the observation. So over the course of a night, let's say. And so that lets you fill in a little bit more of this information space, this Fourier space. But still, there's still a lot of empty space in that picture. And so in order to turn this into a picture of a black hole, they need to be able to do some modeling to go from something like that to an actual image. And so what they did is they broke apart the team, their team into 4 different teams so that they could approach it blindly, and each create software to try and produce an image. And they all agreed in an image that looked basically like this. They combined them to form the picture of a black hole, with which many of you are familiar. Okay. Next, I'm going to be talking about the black hole mass relation. So as I mentioned, these supermassive black holes are the center of all galaxies. And so we want to be able to understand the galaxies and the black holes and how they relate to one another. An interesting thing is found. So to find the mass of a black hole, we'll often look at, as I mentioned earlier, the orbits of the stars going around in them. And so if you came to Emily Leopold's talk over the summer, she talked extensively about this. Basically what's found here, you look at the so-called velocity dispersion of the stars in the galaxy. And because we can't actually measure individual stars the same way that we can in our own galaxy. We can't resolve them. Instead, you look at their bulk motion, and there is found to be a correlation between the mass of the supermassive black hole and the velocity dispersion in the galaxy. Slightly misleading thought. It's not actually a linear relation. It's the mass of the black hole as a function of velocity dispersion. These are both logarithmic scales, but there's still a relation between the two of them. But it's a little bit strange because you can actually also do the calculation and you can see that your central supermassive black hole can't actually have a larger influence on the outer stars than the stars do on themselves. And so, than the stars do on one another, rather. And so it's interesting that there's still a relation between the mass of the black hole and the velocity dispersion of the whole galaxy when they're really only gravitationally influencing, at least when it's a majority, they're closer, about 10% of their galaxies. But we're still able to use these sorts of measurements to be able to look at the masses of the black holes at the center, the supermassive black holes at the center of galaxies. So the last concept that I'm going to talk about are quasars. And so these quasars are when you have a supermassive black hole at the center of a galaxy, it's going to accrete matter from around it, the stars, gas, dust, and it creates these powerful jets that can outshine the entire galaxy. It can be 1,000 times brighter than the whole Milky Way and also outstretch the whole galaxy. And so these tend to be active in galaxies that are rich in gas. And they're very easy to measure because they're so bright, though they are harder to understand. And we think that the mechanism that powers these quasars must be black holes due to their immense energy. And they also likely cause what's called feedback. There's feedback between the gas that they produce and gas they take away, and this affects galaxy evolution. And so all these things kind of come together in the puzzle. And so understanding them and all sorts of other supermassive black holes and stellar mass black holes helps us to get a better picture of the black hole landscape and the physics landscape in general. It helps us understand astrophysics from galaxy evolution to stellar evolution, supernova physics, so that's when the physics of exploding stars. It can help us also push fundamental physics, so understanding general relativity and the orbits and stuff, or understanding orbits and gravity in a deep way. But something that we need to really understand very deeply is our biases in understanding these. Some of the most obvious ones are, in the case of X-ray binaries, you're not going to be able to find objects that are, a star and a black hole separated widely. And so there might be other things that our methods aren't able to touch. And so that's why often astronomy is a very discovery-driven or data-driven field. Whenever we turn on a new telescope, we learn a ton. Lots of unexpected things. So we're in an exciting time. Lots of new telescopes coming on. So in summary, black holes are these bodies of immense density from which light cannot even escape. Black holes less than about 100 times the mass of our sun are these stellar mass black holes that come from stars. And we can find them using X-ray binaries, microlensing, gravitational waves, and astrometric binaries. And these supermassive black holes greater than 100,000 times the mass of our sun, we can find using stellar motion, radio interferometry, velocity dispersion, and quasars. Thank you.